Hello and welcome to the AI Research Roundup. I'm your host, Alex. Today is May 10th, 2025. We're diving into an ICLR conference paper on the Hölder stability of multiset and graph neural networks, published just over 3.5 months ago. This paper investigates multiset and graph neural networks. These are AIs for complex data, like item collections or connected structures such as molecules. It looks at how well these models truly distinguish different inputs, going beyond just theoretical guarantees. The authors propose a new way to measure this ability, called lower-Hölder in expectation, to really quantify the quality of separation in these networks. Okay, so to really see this issue of separation quality, the figure plots, quote, embedding distance. That's a measure of how differently the model represents two inputs, against network width, which is like the number of internal processing units. For networks using what's called a rectified linear unit, or ReLU, activation function, a common type of mathematical switch, the embedding distance or separation starts incredibly small, but then sharply increases with more width. In contrast, smooth activation functions show consistently poor separation here. The dashed line, labeled W_1, likely shows the ideal separation achievable by a standard graph comparison method, the Weisweiler-Lehmann test. Building on what we saw with activation functions and separation, this table summarizes theoretical lower-Hölder exponent bounds. This exponent, alpha, quantifies separation quality. A smaller alpha, ideally 1, means the model better distinguishes different inputs. For multiset functions, which handle item collections, sort-based methods achieve that ideal alpha of 1. Then, for message-passing neural networks, or MPNNs, AIs learning from connections in graph data, the sort MPNN model also hits alpha of 1. In contrast, smooth MPNN and ReLU MPNN models have exponents that can worsen with network depth, k, indicating poorer separation. So, these bounds clearly show architecture choice is key for good separation. Alright, so these next plots really bring those theoretical bounds to life. We're looking at 4 graphs, each plotting embedding distance. That's how differently the model represents two inputs against multiset distance, which is the actual difference between two collections of items. For the sigmoid function, the line, with an alpha of 16, is very flat initially, indicating poor separation. The rectified linear unit is better with alpha at 1.5. But the adaptive rectified linear unit and the sort-based method, they both achieve that ideal alpha of 1, showing a nice straight line. This visual evidence strongly supports the theoretical findings we just discussed, especially for those superior methods. Okay, so this table then tests these ideas on a really tricky task, epsilon tree binary classification. These epsilon trees are special graphs designed to be hard for typical message-passing neural networks to tell apart, even though a standard graph comparison method, the Weisweiler-Lehmann test, can distinguish them. And look, established models like GIN, GCN, GAT, and even the ReLU MPNN and smooth MPNN, they all get an accuracy of 0.5, which is basically random guessing. But the sort MPNN and adapt MPNN achieve perfect accuracy, 1.0. This really drives home how important that better separation quality is. So after seeing how sort MPNN and adapt MPNN excelled on those tricky epsilon trees, this table shifts focus to more standard graph learning benchmarks, specifically a collection called TU datasets. We're looking at classification accuracy, which is just how often the models correctly categorize different graphs across several datasets like MUTAG and proteins. The sort MPNN and adapt MPNN are up against established models, and you can see, often in bold, they achieve very competitive or even the best results. This really shows their improved stability and separation capabilities translate into strong general performance. Building on that strong performance on standard benchmarks, these next plots take us back to those challenging epsilon trees. We're looking at embedding distance versus tree movers distance, or TMD, which is a measure, based on the Weisweiler-Lehmann test, of how different two of these special tree-like graphs are. You can see for sort MPNN and adapt MPNN, the lines are straight, with that ideal alpha of 1, showing great separation at both network depths. But for smooth MPNN and ReLU MPNN, the alpha value gets worse as the network gets deeper, meaning their ability to tell these epsilon trees apart really degrades. just as the theory predicted. So, to bring this all together, the key takeaway is that for these AI models, working with complex data like graphs, it's not just about if they can tell things apart, but how well they do it. This research introduces a really neat framework called lower-Hölder in expectation, which is a way to measure the quality of this separation by looking at the ratio of how different the outputs are compared to the inputs, where a lower exponent in this measure means better, more robust separation. This helps us understand why some standard message-passing neural networks can lose their edge, especially with deeper networks, while innovative models like sort-MPNN and adapt-MPNN maintain strong, stable performance. That's it for this insightful paper. Thanks for tuning into AI Research Roundup.